Okay, hello everyone. Welcome to this session about SQL streams and Materialize. I'm Marta. I'm kind of terrified for numerous reasons. One of them is that I'm about the same weight, same height as this stand. But I guess as long as you can see my screen, my terminal, that's the most important thing. I would like to start just by saying that I'm not going to rock your world with some new exotic flavor of SQL. Everything that will be discussed and demoed in this talk uses the same SQL that you know and have used since the beginning of times. So that means that if a statement like this makes any sense to you, you also already know how to write SQL that runs on streaming data. But this would make for a pretty short talk, right? So what I'm hoping to get across is show you how you can build streaming applications using nothing more than SQL with Materialize. Let's start from the beginning and kind of work through some familiar ground. So to make sure that everyone can follow along, understands how we get to a point where the idea of using SQL to handle continuously produced data makes some sense. So the first step is to think about an OLTP engine, or the traditional relational database from back when databases were first created. It's designed for high concurrency with lots of reads, lots of writes, and transactions happening at the same time. And in general, this kind of system works very hard to make sure that your business data is consistent and available. But because OLTP engines are also kind of good, or at least good enough at other use cases, it's kind of common that they're used as a one-stop shop that can also answer questions about the data that you put in them. So if you use a database like MySQL or Postgres to store your product inventory and orders, for example, you might start out by also running some analytics on it. And this might be fine. Maybe your data volume and speed aren't that high yet. Maybe you don't have that many users accessing the system concurrently either. But at some point, this will stop scaling well. So after all, analytics workloads are very expensive and will start slowing your database to the point where it starts affecting its actual primary use. So your read and write throughput might go downhill, your database may even become completely unavailable, and suddenly the idea of using a single database for everything kind of starts sounding like not such a good idea. But these nasty workloads that are eating into the performance of your database are really exciting and valuable for the business, so folks still want to keep using them. What do? The next step might be to something like offloading things to a second database that is built maybe in a way that is more appropriate and more friendly to analytics workloads. And this is usually an OLAP store where you don't have the same strict requirements for concurrency or availability, but you have different requirements like supporting heavy-duty operations like multi-way joins, subqueries, aggregating over large collections of historical data, and so on. And this represents a totally different set of things that your system needs to optimize for. So now you have two separate systems, the transactional processor on one side holding the source of truth for your data, and the analytical processor on the other dealing with complex questions on top of your data. And because they have different things to optimize for, like I said, they also end up having very different designs. So OLTP systems are generally row-based, which makes them really, really fast for writes, but a bit slower for reads that go over just like very simple operations. And OLAP systems are normally columnar, so the data is organized in a more attribute-oriented way. That makes them very, very fast and efficient at serving heavy analytical requests. And overall, compared to where we started from, doing everything on top of your OLTP database, things cool down a little bit. But still, at some point, you may start having issues with your OLAP system as well. So as users start asking more and more questions, also more complex questions, maybe you start having ingesting data that is coming at a higher speed and higher volumes. So the problem isn't really solved. All we did was really kind of pass the hot potato from one system to another. Though, at least now the impact would be more on the side of your business stakeholders than on the actual availability of your whole business. And this kind of brings us to Materialize. So if we think about this problem in a different way, we can think of our OLTP system as being pull-based. It's just sitting there, waiting to be queried. And on the other side, we will have Materialize, which is push-based. So what this means is that instead of just sitting there like the OLTP database, Materialize will proactively react to any changes that occur in the input data. It will maintain the results of your computations for questions that Materialize knows you want to ask frequently and repeatedly. And it will keep whatever you have downstream fresh while keeping the amount of work that it has to do to accomplish that to a minimum. So you can look at it, or you can call it online view maintenance. In practical terms, what this means is that you can just tell the database, hey, I'm interested in asking this question over and over again. Can you please pre-compute it for me as data changes, so I always get correct and fresh results whenever I hit it? And this way, we don't have to pretend to be surprised that we're seeing the same query being issued for the 100th time. The processor can just go ahead and incrementally maintain the results as new data comes in, instead of calculating them from scratch every time based on snapshots that might not even be fresh anymore. So as an overview, Materialize is a database that is optimized for view maintenance over streaming data. And we're calling it a database because it really walks and talks like one, like you will see soon in the demo. And it still supports all these heavy, complex workloads we wanted to run before. So it lets you ingest data from multiple types of sources, so like streaming sources, historical sources, even CDC streams. You define some transformations as SQL queries within Materialize. Materialize efficiently maintains the results to whatever query you throw at it as new data streams in. And this means that instead of waiting for your ETL jobs to run to bring data from your OLTP database to your OLAP store, which can take hours, you can kind of put your results to work in real time, either by directly connecting to BI tools, syncing to Kafka for event-driven use cases, or streaming it to applications interactively. And this is a lot of talking already, so let's actually get our hands down and see a real-world example that hopefully makes some sense. So here we'll be looking at gaming data streaming in from Twitch. Sorry in advance for putting together such a meta demo, because this is basically just looking at streams of streams. And I only realized later on that maybe that's a bit confusing. So I will just refer to a Twitch stream as a broadcast from now on. And the whole setup is going to be running on Docker, so everything can go very wrong very fast. And this is available, so if everything just goes up in flames, you can just go to GitHub and you can try to run it yourself without having two screens and a bunch of people looking at you. Cool. So what we're doing here is just build an end-to-end analytics pipeline that grabs active gaming broadcasts from the Twitch API. It kind of just trickles everything down into a live dashboard on Metabase. And we have quite a few services involved. So let's start with our sources of data. We have Kafka and Postgres as sources of data in our pipeline. So for Kafka, there's very rudimentary data generator. There's just like a small producer written in Python. It's just fetching data from the Twitch API. And in Postgres, we will have some reference data to enrich these events. And then we have Materialize, the whole point. So we will use to ingest and transform all this source data using SQL. And in the end, we just dump everything into a dashboard. And if this is your first time hearing about Materialize, or you're kind of completely new to streaming, it sounds like a lot of moving parts, but if you're looking to get started with Materialize, you can just locally install it. It runs as a binary, so and just get very quickly a much simpler setup, Kafka-less. Just plug it into the replication stream of Postgres or something, and suddenly you have a streaming pipeline. Another quick note to avoid confusion: I'll be using Red Panda here as a drop-in replacement for Kafka, mainly because they have Docker images that run on ARM, and I didn't really want to increase my odds of completely failing here by relying on a virtual machine. Oh, okay, it's time to move. Okay, so to get started, we can bring everything up. I think I did bring everything up. Whoops. A few minutes ago, but whoa. So it starts. I think everything is up. Of course, the data generator is not working, but let's fix that. Okay, I'm just running the data generator because, having a scheduler inside Docker running this very frequently was also kind of a risk. So I think now we should be good to go. If I can find my laptop, yes. Okay, so everything is up. Let's see if we have, the producer is supposed to create a new topic on Red Panda called Twitch streams. It's there. We just need to make sure now that it's also getting data from the Twitch API, which is happening too. So things work, good news. If you look closely at the structure of the events, these are basically broadcasts that are being pulled in right now from Twitch. And they just have basic information about active broadcasts on the platform right now. So you have the broadcast ID, you have some user information, the username, the game that they're playing. Oh, this is cutting out. Okay. The game that they're playing, we have the starting time of the broadcast, and so on. So now we're kind of ready to go to Materialize land. Should I reduce this a little bit? Okay, here we go. Cool. Oh no, it's showing all my clears. So we first need to connect to Materialize. And because Materialize is Postgres wire compatible for end users and applications, it just feels like interacting with a Postgres instance. So one way to connect would be to just use pSQL. Here I'm just going to use the MZ-CLI. It's a SQL shell that is based on pSQL too, but for Docker it works a little bit better. So this is Materialize. Oh no. Okay. This is Materialize. Maybe I can. No. Clear things. Yes. Cool. So we're in Materialize. The first thing that we need to do is to tell Materialize how to find and connect to our data sources, which are Kafka and Postgres, like we went through before. And so for Kafka, we'll have a Kafka source consuming data from, it's pointing to our Red Panda broker. It's going to read the Twitch streams topic that you just saw coming down a bit before. And if you noticed from the events, something that is kind of inconvenient is that the events have embedded the viewer count, which means that whenever a broadcast, whenever people join or leave a broadcast, you will get a new event for the same key. So this is why we are telling Materialize that it should work in upsert mode, so that when an event comes for the same key, Materialize can just override it and make sure that we only keep the latest viewer count for each broadcast. So that's it. We created our Kafka source. The data is stored as raw bytes, so we also need to do some conversions to make it readable. I'll just kind of gloss over it and paste this monster query here, and then clean everything so that you don't have to look at it. But basically, this is just converting data into JSON. And now for Postgres, we are going to connect to it and directly consume its replication stream. So we'll be doing change data capture. And the idea of using the source in kind of like this mode of ingestion is that the official list of tags on Twitch is managed by Twitch itself. So in the real world, we would want to instantly replicate any changes to this list into Materialize to kind of be factored into whatever computations we are maintaining there. So if a new tag is added or a tag is deprecated, a description is updated, we just make sure that we stream that into Materialize as soon as it happens. So we could also do this, since we're already using Red Panda anyways, we could do exactly the same thing using Debezium. But I just wanted to show an alternative way in case there are people, again, here who don't really run distributed systems and couldn't care less about Kafka. So this is a syntax to create our Postgres source, and as soon as we're done with that, we can just do show sources, and we see that the sources are listed in the Materialize metadata catalog, which means that we're ready to start asking questions about this data. So the rule of thumb in Materialize is that you want to create a materialized view for questions that you want to see answered repeatedly, but fast. Speaking of fast, let me turn timing on so that we can see how long things take. So let's start by figuring out what the most popular games are on Twitch, like games that are on right now, based on how many viewers are currently watching. So to do this, we create a query with a basic aggregation over our Kafka source based on the game ID and the game name. And we are just grabbing the sum of viewers as well as the number of streams that are currently active for each game. So once we create the Materialize view, what Materialize is doing in the background is it's indexing the results in memory, and it's incrementally updating them as new data comes in from Twitch. So when we hit it with random queries, we can get the results out really fast. So for example, if we want to see the top 10 games that are streaming on Twitch right now, we can just use our newly created Materialized view and just say, hey, give me the top 10 games with a bigger viewer count. And Materialize will say that people are really into just chatting and Counter-Strike and Fortnite, Minecraft. So it's kind of like very predictable list, I guess. But the idea here is that if you reissue this query over and over again, you will see that the results are changing as new data streams in. I'm not sure if this will be the case because I think, wait, we should see that. So let me run the data generator again, and hopefully, so see, you can see the results are changing, and you can see that Materialize is coming back to us with millisecond latency with updated results. Cool. So this is a bit hard to see on the shell, but like once we move to Metabase, it will be a bit more like the evolution will be a bit more apparent. But the point here is that Materialize is now maintaining the aggregated results in memory as it receives new data. So any query that you put on top of it returns in milliseconds. So let's have a look at what happened under the hood when we actually created a Materialize view. So let me, yes. So if you do show materialized views, we have the materialized view we just created here. But the little trick in Materialize is that when it creates a materialized view, it also creates an index. So this is how data is stored in memory in Materialize. And at this point, you might ask, how is Materialize actually maintaining these indexes up to date in memory as new data arrives? And the heavy lifting is all done by its core computing engine. So it's a project called Timely Data Flow, entirely written in Rust. It's based on a bunch of years of academic research. And if we look into a little web server that Materialize exposes, if I can find the right tab, not this one, this one. We should be able to find here the view we created, I hope. Oh, yeah. OK, so it's not working right now. I kind of expected this. But basically, what you would see here is the data flow that Materialize generates when you create a materialized view. So it's just basically a bunch of operators that each event goes through, and that kind of trigger computation if anything changed in our source data. So I'm sorry I can't show it right now, but hopefully you can visualize it. OK, coming back here. Yeah, the thing also with the data flows is that as a user, you don't really have to care about any of this. So it's actually good that it can't see it, because you should not have to care about the data flows that are generated by Materialize. All you have to do is write SQL queries, let Materialize handle the rest. So this is what the core of Materialize is. There's some timely data flow magic involved, but in the end, all you have to care about is just writing SQL queries and kind of delegate actually updating, keeping the results up to date to Materialize. So next, we're going to look into a couple of patterns that only become interesting when you apply SQL to streaming data, and that you might assume you would need more than SQL or maybe some custom SQL extensions to achieve. Imagine that we want to look into what broadcasts happen in the last 15 minutes. So one of the more immediate differences in streaming is that time keeps ticking along. So as we sit in this room, the same is true for data. So unlike what you may be used to with batch, where your data is sort of frozen at query time, this means that if we want to ask something like, what happened in the last 15 minutes, in the last 15 minutes is actually a moving target that changes as time moves forward. So how do you express this in SQL? In Materialize, you can use something called Temporal Filters to define. Here, what we have is a sliding window. What it does is it expires events progressively as they fall outside of this time period. And it picks up new ones with the bonus of not having to learn new syntax. So like windowing, you just use a where clause with a bunch of filters. So the key here, or the secret to actually making this happen, is MZ logical timestamp, which keeps track of the logical time of your query under the hood. You can think of it as like now works in Postgres or in MySQL, for example, but kind of like ported into the streaming world. So if we create this materialized view, now we can check some streams that actually satisfy this condition of not having started more than 15 minutes in the past. So we just say select star from this Materialize view, order it by the started date, give us just 10 so that it doesn't look ugly. Okay. And you can see the started date here. You can look at your watch and see if it makes sense. And we can see if Materialize is doing its job by just looking at the minimum date, at the minimum starting date from the Materialize view. And you see that as time goes by, it's also expiring events that have timestamps that are lower than that. So that is time in Materialize. Cool. So I have 5 minutes left. Let's actually go through another interesting, somehow feared pattern in streaming, which is doing joins between multiple streaming sources. In our case, if you remember, we have a Postgres instance with a bunch of reference data. And we kind of want to use that to enrich all these events that are flowing in from Twitch. So what we can do is just create a little aggregation of our Twitch data so that we don't have to cost more in the join than necessary. And then we can join it with our CDC source from Postgres on the tag ID, which is a UUID, so it doesn't really tell you anything when you try to do something, so to learn something like what are the most used tags. So if we create this Materialize view, what you can see next is that we can do select all from moving. Oh, why did I name this so weird? Stream tag, order by, contact desk, maybe 10. Okay, so these are, so now we have the actual human readable description. And again, if we turn on our data generator, Materialize is just in the background, like keeping this join going as data changes. And this is really one of the highlights in Materialize. It can handle 8-way, 16-way data warehouse grade queries in a pretty efficient way, and with much less restriction than other existing streaming systems. And to finish this off, I would like to show you a dashboard feeding from all of these Materialize views that we created, but I don't think Metabase will be cooperating. So, well, it kind of is. So I have a GIF, which I hope also does. So this is what, if I had time to do a whole dashboard, it would look like. This basically works without any other intervention from you. Materialize is just keeping everything up to date, correct, and fresh as new data comes in from the Twitch API. And yeah, now I just need to kind of send it off. Okay, so too long did it read for this talk. Materialize lets you build streaming applications using SQL, takes care of all the heavy lifting for you. The 4 things to keep in mind is that it allows you to ingest data from a wide range of sources. So like you can ingest from streaming sources. You can also bootstrap your streaming. You can also bootstrap your streaming pipelines with historical data from S3, for example. It allows you to query in standard SQL. So if you just want to port queries you have currently today on Postgres to Materialize, it should be pretty straightforward. There are no weird extensions, no new syntax, no sugar on it. It's just standard SQL. it works by incrementally maintaining views for you for whatever data you're interested in, while doing the minimum work possible. And because it is PostgreSQL compatible, out of the box, you already can connect to the whole Postgres ecosystem. And you can even use Materialize with dbt, for example. So this kind of expands the audience that can actually use streaming without actually having knowledge of distributed systems or any of that. So yeah, if any of this was interesting, feel free to try it out. Materialize is source available, so you can just brew install it if you're on a Mac, play around with it. You can go to my GitHub and run the Twitch demo yourself. And yeah, if anything rings a bell, join the community. And yeah, thanks.